Hello, I'm Roman. Welcome back to the series of the videos Neural Networks from Scratch in Go, where we using the book called Neural Networks from Scratch in Python. But as you can guess again from the name, we are writing everything with a Golang. And in the previous video, I finished with L1L2 regularization and I started to dive into the next chapter, which is called the Dropout, where we need to implement the new type of the layer that's supposed to filter number of the nodes used for during the model training and the forward and backward pass. So we kind of studied all of the material to do this. And right now what I need to do, I need to implement the next layer. This is what we're going to do. So I think we'll start from the dropout, then testing it. And this is the whole code. And then probably we'll go for the next one. But let's see how it will go with this one. And if you missed, I published a video on the YouTube channel, on the main YouTube channel, and it's about what type of the maths you actually need for software engineering. So instead of talking about this that you need math, you need to know math to do software engineering, I actually tried to show several examples that are pretty commonly used. So I would appreciate if you will take a look. So okay, let's go and try to implement this. So what I need to do? I have the layer, so I'm going to use the dropout layer, and there is a package for it. So what we're going to do? We need struct dropout layer, right? And what we will need to do? We'll definitely need inputs, outputs, and the inputs. So for example, if we take a look at the layer, so we will need inputs, right? So we'll need inputs, and we go in, I think it should be private, oh, yes, because it's struct. Okay, the next thing is the output, right? Output, dense. Then we should have, or actually we need a binary mask. I think this will be private. It's called binary mask, but I don't like the name, but okay. I just call it mask. It's not that better too. Okay, binary mask. And same. With the outputs, we will need the inputs because we will use it in another place. Okay. So then we will have how many? One, we will have the initialize method. Oh, and we need to have a rate. Rate, and it should be floating point type. So okay. So I actually am not sure that I need to make an initialize. Yeah, okay. I will do this just to be consistent with the style. So first it will be a dropout layer, then it will be rate plot 64, and then we assigning the rates to the input parameter. And then we're going to have the forward methods, right? But again, for the dropout layer, and we should have the backwards, right? We should have the backwards, which is same. And as long as I can see, it will be the same. So this one takes inputs, this one takes d values, right? Okay, actually, this one is this. So the rate is actually a dropout rate. So for the inputs, well, first I need to store the inputs. So we use a layer inputs and we're storing the inputs. Then we need to create binary mask. And this is interesting because the binary mask is, well, using the binomial, and that's what I've been checking previous time, and it uses this size of the input shape. So it should return, the binary mask should be the two-dimensional one. So I think that should be dense copy of inputs, right? And then what I'm going to do, I'm going to use my favorite apply methods. And I mean, it makes the copy, but I don't need to use the value itself. And what I'm going to do, I need to have the binomial of the dropout rates divided by the rate. What's called scale up values. Okay, now I remember. So we're going to use, where is it? I think this is here. So what I need this binomial from the binomial. It doesn't know this one. It's in gonam stat gonam stat and combine, right? Then generalized binomial returns a generalized binomial coefficient of a and k, where is the gamma function. Okay, let's try. So in our case, n should be 1, and this one should be layer rate, right? And then divided by divided by rate. Okay, and then we need to multiply what do we need to multiply? We need to generate the output. So the output will be, it's actually interesting. Do I need to pre-allocate this, or if I will call something like element-wise multiplication, it will do the same. But okay, layer mul, I think. Yeah, mul takes the product of A and B, placing the result into the receiver. Yes, it will panic. So the first one is, what is it? Inputs. The second one is layer binary mask. And that's it. Right. By the way, this is what I'm curious. No, I think it it assumes that M already has some data. Check overlap. Yeah. Okay, then with the backward method. And with the backward method, we only need to create the D inputs, which is the inputs, which will be copy of the values at first to allocate this, and then layer the inputs is the multiplication between the values and layer binary mask. The question is first to test this one, and I want to test it first. So let's test it a little bit. So what we have, well, first this one, binary mask, and this I just need to check. So that will be the data set. It could be spiral data 10.3, probably, right? And rate, okay, rate equals to 0.2, which should be 10 minus, and then binary mask. Oh no, that's not the binary mask, that's the data. Then I have binary mask equal to dense copy of data. And then I need to dense multiply between data and binary mask. And then I can print math for methods. Not and binary mask. Okay. Dimension mismatch. Where? Dense arithmetic. Go 100. Oh. How it could be how it could be a mismatch. Okay. Oh, it's a matrix product. No, I don't need the matrix product, actually. Good that I found it. Dropout layer inputs. Interesting was that this product calculate the product of a given factors and places the result there. Oh, okay. Let's. No, the binary mask is... No, it's not what I need. It's not what I need. Okay, what I've been checking? Binomial instead of the generalized. So this one. Okay, this looks... Okay, I took the incorrect one, so it's a gonum stat dist. Oh, um, dist. Dist. Okay, then dist. Binomial. Binomial with n rate. Can't use binomial. And then rent. Too few values, okay. So I need to define the... Where is it? Rent. I think I found it somewhere last time. Oh yes, this one. Right. Um, Hi. Binomial. Can't use SRC. Temperament is Golang, expand rent, subscription string, and doesn't implement round method seed. Okay. Oh, probably because I need this as well. Really? Rent. Yes, it used. Oh, rent. And mm, already cleared. Okay. Maybe. But if I will do this, X rent. Can I do this? Why you're removing this? Oh, okay. Rent. Um, go rent. Okay, that is something. Then here make one. Okay, that looks much better. What if we'll do this? Okay, looks like this is what I needed. So I need to do this. I need to copy this one. Where is it? This one. I will use rand here. I don't have the problem of clashing names. And then I should use this one. Then instead of the rates, I have the layer.rates, and then I forgot to divide by rates. Okay, this is better. So this one is N, this is P, and I think this one is okay. Then what it means? I don't need this testing. I can remove this one, and I should. Okay, let's take a look. I'm creating the binary mask, I'm creating new randomization source, and I'm creating the binomial distribution from the GoNum, and I'm dividing by the layer rate, and I multiply element-wise two arrays, and the backward pass should be much, much simpler. Okay, so then what do? We have the dense layer one, we have the activation one. Oh, by the way, there with 64, I think I will replicate this also because it will, much faster. Okay. Then I have dense one, activation one, and dropout one. So I think somewhere here I should have dropout one, which is the layer layer. Dropout one initialize with 0.1. So we're leaving 90% of the things we should stay the same. During the forward pass, add in the dropout. So dropout takes the okay. So then we have dropout one forward that takes okay, then taking the output from the activation, right? Which means that the second layer should take the output from the dropout layer, right? So that should work. Okay. And of course, in the backward pass, we need to revert this. So we have the dense one, we have the activation one, then we have dropout backward that takes activation D inputs. And no. It takes dense 2, the inputs, and then activation 1 takes from the dropout. We have the dropout, then we have the dropout backward from the dense 2, and we have activation 1 from the dropout. Let's also raise the learning rate a little bit from 2. Okay, I have it already. And decay from decay this one. And decay raise a little bit. As for some reason they should work better with the dropout. So this is the code so far. Let's take a look if it works. For example, the results that they have in the book is validation, the training, like 75%. Training accuracy is pretty low. Okay, let's just check it. Man bed region identical. What does it mean? Dropout. Oh, wait, did I? It's not the inputs, right? It should be the inputs. The inputs. Oh, wait. No. It should be output. Inputs multiplied by, yes. Same error. That should be element wise. Okay, it works. Yeah, I mean, but the accuracy is not that good. Where is it? Accuracy during training, they have around the 68%. Oh, I think I have better because my... Why I have it better? What is the number of the nodes they have? Oh, but I downgraded it to the 64. Let's quickly check. 64. Ah, but no, 1000. I think I have the same. Right? Yeah, 1064 neurons for the hidden layer. Okay. But learning rate is about the same. So what we have? We have the final loss 0.57, this higher validation loss. But I think they should be around the same. Yeah. So I think the main idea is they very close to each other, even that it's pretty small. What's happening with my mouse? Okay, I will do it like this. Accuracy here is 73 and here is 70. So I guess the main whole point was that while our accuracy and loss have suffered considerably, we have found a scenario where our validation set performs better than our in-sample set. Do I have the same? Not really. At least for the data that I have. But I can try once again. Because we do not apply dropout when testing, so we don't disable some of the connections. That's true. Further tricking would likely fix the accuracy issue. For example, due to our regularization tactics, we can change our layer size to 212 or 512. Adding more neurons end up with validation accuracy. So they're pretty good results, but worse comparing to the no dropout model. Interestingly, validation accuracy is close to the training accuracy with dropout. Usually validation accuracy will be higher. So we might suspect there are, as a signs of overfitting here. Validation loss is lower than expected. Validation loss is lower than the training loss. Okay. Let's take a look once again. So I have, interesting, what's happened with my mouse? Okay, so we have the accuracy 66%. The oh, the accuracy is actually higher, 72. We have the loss 0.74. Here we have 0.65. So it's actually true that it's better. So, but if we will, I mean, the validation results are better than the training, but if we'll change for much bigger, that could take a while. Okay, I think there is no point to actually continue training it because I already can see that the accuracy is very high and it's just, you know, 2 from 10,000 of the epochs that we're going to do. And the accuracy started to jump back and forth as long as the loss. So I assume that the model is already overfitting. And I think that's what they've been talking here that, I mean, it looks like, I mean, at least from what is telling here. So if we have the validation loss higher than the training loss, it's a good sign, right? Where it was. Of course, compared to no. Interesting, the validation accuracy is closer to the training accuracy with Dropout. Usually, validation accuracy will be higher. So if the training accuracy and loss is less than the validation one, that's a good sign. If it's higher, then it means that model goes in the direction of the overfitting. And for example, here, I think, well, if I will wait until it finishes, I will see a big difference in the accuracy and the loss. So probably this is a big model for this number of the of data. I can stop it. Yeah. Okay, but I think if we will, I mean, maybe not 64 neurons, but twice more, then I think it will be better. Also, I want to check that okay, the weight regulator in this one, bias regulator is the same. Dropout is the same. So, okay. And as usual, in the end of the chapter, I'm checking what is the sample code. So this is the whole code, or at this moment, it's actually pretty good amount. And so we have this chapter 1670. Oh, chapter 22. Okay, final. Probably this is, whoa, okay. Twice bigger. That's good. That's good. It means that we still have a lot of things to implement. Okay, I will stop here for today. It was a pretty disturbing session. I had to be disturbed many times, but it happens. And that means that I will see you tomorrow implementing the binary logistic regression. So I see you tomorrow. Bye bye.